So in the previous lessons we've been looking at polynomials and doing arithmetic on them. We're now going to move forward and we're going to learn how to solve and factor polynomials. So let's just look at quadratics first. When we had a quadratic equation, say something of this form, what we did first was we would make it into a form where one side has a 0, and then we would factor the other side, and then set either of these two terms to 0 by the zero property theorem to find our two solutions for the equation. We can extend this idea to all polynomials. So if we had something like this, it's a more complicated polynomial. We do the same thing. We move terms around and we have an equals 0 on one side and a standard form polynomial on the other side. And if we could factor it, and we're going to get into how we factor it, but if we could factor it down, then we could do the same thing. We could set each of the factored terms to 0, because if any of these are 0, then this left-hand side will be 0. The product will be 0. So we have, in this case, three different answers. X is equal to 2, 3/2, or negative 3/2. So the key idea here is if we can factor, then we can solve. We need to figure out how to factor polynomials now. There are four different methods that we'll be looking at in terms of how we factor polynomials. And when I say factor polynomials, we're going to need to factor it completely. And what that means is we keep on factoring until we cannot factor it anymore, until there are no more opportunities to factor with integer coefficients. So we have a method called common factoring. We have a method called special patterns, grouping, and quadratic form. So we're going to go through each one of these one by one. Common factors. We always do this first if possible. This is something we do for all the cases, no matter what. It simplifies our numbers. It makes things easier to deal with if we can factor out some terms. So look at this one right here. We have a common x term in every single one of these additive terms, so we're going to factor that out, and then we can continue factoring. So we notice that this polynomial here, after we've factored out the x, is something that we can still factor. So we continue forward with just the methods we learned before in the past. Let's look at a slightly more complicated one. In this case, we do see we have 5 x's here, we have 3 x's here, so we could factor out x to the third. But we also need to look at the numbers. We have 2 even numbers here. I could factor out a 2. So altogether, I can factor out 2x to the third power. So as I do this, I have an x squared term here. Think of it like this. I have 2x to the fifth divided by 2x to the third, and that equals my x squared. I could also do the same thing for the next term. I could think of this as 2 divided by x to the third, and then I get my 9. X to the third cancels out. 18 divided by 2 is 9. Now I can continue on here as well. X squared minus 9 is my difference of perfect squares. I could turn this into x plus 3, x minus 3, and now I'm done. So that's common factoring. Always, always, always do common factoring first. Special patterns. As we just saw, there are some special patterns which help us quickly factor. We have the difference of perfect squares, which we just saw an example of, and we've done this in the past. We also have difference of perfect cubes as well as the sum of perfect cubes. So in this case, we have these two patterns that we can use, and we could prove these out, but we're not going to do that right here. Let's see how we can use them here. You notice also that the special patterns that we're looking at, there's just 3 types, and they just have 2 terms each. So let's look at this one, x to the third plus 64, and when we see x to the third we think, oh, that's a perfect cube. So is 64 a perfect cube? As we think about it, we realize it's equal to 4 to the third power. It's the sum of perfect cubes, so we can apply this pattern right up here. So we're going to write this as a template down on the bottom, and we're going to think of our a as x, as our b as 4, and we just kind of plug in at this point. We substitute in all the different values, and we get our factored form here. A little bit slightly harder case here. It might not look immediately that we have difference of perfect cubes here. But again, the first thing we always do, factor out some common terms. And in this case at least, I see 2x's here, I see 5x's here, so I could factor out x squared. These are two even numbers, so I could factor out at least 2, so I'm going to start with that. I divide everything by 2x squared to factor it out. I get left over 8x cubed minus 125. Now I realize, I think I might have perfect cubes. 8 is 2 to the third. 125 is 25, or 5 to the third power. So we can write this as the difference of cubes, and now we can go ahead and use our special patterns to expand this all out. Replacing everywhere, we have our a, which is 2x, and our b, which is 5, so we replace that into the pattern that we have, and then we could simplify that out. So this is how we use special patterns. Again, special patterns, 2 terms, and these are the 3 types of patterns that we need to recognize, no more than these. Grouping. Grouping, we always look for 4 terms. So here's an example. We start with 4 terms, but we group them in 2s. We have this first term over here, and we factor out anything common. There's an x squared that we could factor out of both, so we do that first. We then look at the next term. Here, there's no x's we could factor out of both, but there is 16 that we can factor out of both. So we're going to factor out a 16. Now conveniently, and this is when grouping works, we notice here that we have an x plus 3 and an x plus 3, which itself is a common factor. So we can now factor out the x plus 3, and we're left with x plus 3 times x squared plus 16. We get the x squared from here, we get the 16 from over here, and this is how we factor out the x plus 3. Let's look at a slightly harder example. And the only thing that makes this a little bit harder is we have these minus signs here, and this is the little tricky thing. So let's start with the first 2 terms. We have a common x squared that we could factor out, and now here, let's be careful. We're going to factor out a negative 9 out of both of these. Negative 9x divided by negative 9 is x. Negative 63 divided by negative 9 is positive 7. So we have to be very careful about the signs, and if we do this right, and again, if grouping works, grouping doesn't always work, but in these 2 cases it does. We see we have a common factor term here. We have the x plus 7 in both cases, and so this allows us to continue on and factor out the x plus 7 portion, and we're left with x squared minus 9, which we could see up here in blue. Conveniently, we factor it out like that. And this is not our final answer because we can continue on. X squared minus 9 is our special pattern, difference of perfect squares, and we can now factor this down to x plus 7, x plus 3, x minus 3. So that's grouping. Again, look for 4 terms. We group them into two groups of two terms, and we look for common factors in each one of those. Our last method is a method that we call quadratic form, and in this case we look for three terms, and these three terms need to be special. We need to look for what I call a quadratic signature. Now recall, quadratic equations or expressions have this x squared, x to the first power, and then a constant. You can almost think of it as x to the 0 power. But the key thing is we have an x to the second power, x to the first power. That's the quadratic signature. Now in this case over here, we don't exactly have that. We have x to the 6th, we have x to the 3rd, but there's a 2-to-1 relationship. 6 is twice 3, just as 2 is twice 1. And then over here we don't have anything. There's no x term here. There's no x term here. So we can use this method called quadratic form, and the method is this. We're gonna substitute. We're gonna say let w be equal to x to the 3rd. And now we're going to do some substitution where we say instead of x to the 6th, we're going to express that as w squared, because x to the 3rd squared is x to the 6th. Then we have minus 5, and instead of x to the 3rd, we write w minus 6. And now we have something in clearly quadratic form, and we can think about, can we factor this? And yes, we can. This is a straightforward one to factor, w minus 3, w minus 2. Now we're not done. We need to substitute back. We're going to, every place where we see w, we're going to replace it back with x to the 3rd. So we do that, and we're done. We don't have any opportunities to continue factoring this down. Another example, last example. In this case here, it doesn't quite look like the same thing up here. We have m squared term. Here we didn't have anything. But we notice that we can factor out the common terms. There's an m squared in every single one of these. So let's start off always by factoring out the common factors. We have a common factor of m squared. So we factor this out, and now we see this signature. We see a 4, we see a 2. So now that we see those, we have an opportunity to do kind of this quadratic form method, and I'm going to do it this way. I'm going to let w be equal to 6m squared, because I also noticed that 36 is a perfect square, and so this is a little trick. It sometimes works. And so instead of w being m squared, I'm going to say let w equal 6m squared. So then I can replace the 36m to the 4th by w squared. And then 12m squared is actually equal to 2w plus 1. Now this is a very straightforward equation to factor, so I factor this out. This is actually a perfect square trinomial, w plus 1 times w plus 1. Now I need to substitute back. I take the 6m squared, replace it everywhere I see the w, and then I'll just write this as a squared term here. So m squared times 6m squared plus 1, quantity squared. That's our final factored form. So that's our lesson. You can go ahead and try these problems on your own. We'll do these also in class tomorrow. Okay? Have a good day.